with the Southern Climate Impacts Planning Program at LSU. Hal, if you've got control of the PowerPoint, I'll let you take it from here.
Well, thanks, Bill. Sorry for everyone for the delay. Bill, now you know why no one ever asked me to do a webinar, right? Because of my technological skills here. So anyway, I'm just joking. Thank you so much for the invitation, and thanks so much for everyone making this a part of your day. I'm excited to share some of our research here with the Southern Climate Impacts Planning Program. We're a NOAA-funded program. We're focused on weather and climate impacts in a 6-state region, including Oklahoma, Texas, Arkansas, Mississippi, Tennessee, and Louisiana. I've been focused on research here along the U.S. Gulf Coast, really doing the whole Gulf Coast, but particularly I'm focused on Mississippi, Louisiana, and Texas. So I'm going to be sharing a presentation here called a data-driven storm surge analysis for the U.S. Gulf Coast. And really, storm surge is such a severe catastrophic hazard that it's something that really warrants a lot of study and analysis to understand the vulnerability that we face to this hazard. If we're going to talk about storm surge along the Gulf Coast, a great place to start is with Galveston, Texas. So Galveston was actually one of the wealthiest cities per capita in the U.S. in the late 1800s. However, unfortunately, in September of 1900, Galveston was struck by a Category 4 hurricane that produced a 20-foot storm surge. The storm surge washed over most of the island and actually killed around 8,000 or even slightly more than 8,000 people in the deadliest natural disaster in U.S. history. Unfortunately, storm surge is a problem all along the Gulf Coast. This photograph here, the top photograph is a before picture of the Richelieu apartment complex in coastal Mississippi before Hurricane Camille. And the bottom picture is what was left of the apartment complex after Camille. And we can see the force of water and waves is sometimes so catastrophic that it completely wipes away buildings, and all that's left is really a slab or a foundation. And of course, more recently, Hurricane Katrina produced the largest storm surge in the history of the Western Hemisphere. Storm surge levels were around 28 feet in coastal Mississippi. On the eastern portion of New Orleans, storm surge levels were around 18 or 19 feet, which was well high enough to overtop the levees and compromise the levees. About 80% of New Orleans flooded. Many people drowned from storm surge, and it really gave the idea of how catastrophic this hazard can be in a major metropolitan area. So what is storm surge and why is it so catastrophic? I like this diagram from the Australia Bureau of Meteorology. It shows on the left here, typically we have what we call mean sea level. This is really the average height of the sea level, and we have slight oscillations for low and high tide. However, on the right here, we have a storm surge event in which strong onshore winds actually increase the entire sea level. So when we talk about, for example, a 10-foot storm surge, we're not really talking about the waves. We're actually talking about raising the sea level by about 10 feet. And on top of that, we have large destructive waves, which then really provide a lot of force to smash into coastal buildings. And so that is exactly why a storm surge is such a catastrophic hazard. When I came here in 2008, I noticed that there was no storm surge database for the U.S. Gulf Coast or the United States or even anywhere in the world, and I was confused why that was. I was wondering if there were data out there. I started doing a search of government data, for example, and I found that there were data all over the place. They were just very scattered. So, for example, from the U.S. government, we have a lot of data provided by NOAA. For example, the Hurricane Center provides tropical cyclone reports that go back to 1958, and many of those reports contain many storm surge or storm tide observations. USGS has been doing a great job of deploying mobile tide gauge sensors since Hurricane Rita. So they'll go out before a hurricane hits and they'll deploy maybe 50 or 100 or even more mobile tide gauges that record water heights, and then they will provide those information usually a few months later in a report. FEMA has gone out since Hurricane Katrina and collected hundreds of observations per storm surge events. For example, they'll send teams into devastated areas that go in and measure high water marks, and they'll put those in reports that are very useful to understand what the height of the storm surge was in different places. And the U.S. Army Corps of Engineers, I was surprised to find how great of a data source that they are, especially in the earlier part of the record. So if we go back to the late 1800s, early 1900s, we find a lot of old historical U.S. Army Corps maps that provide some great details of storm surge events from the past. This actually is a map from the U.S. Army Corps from a hurricane that struck the New Orleans area in 1915, and we can see here the track of the hurricane here is a solid black line. everything that's shaded in gray here was actually inundated by salt water. So this is really the extent of storm surge flooding. And it may be difficult to see, but there are actually many observations along the coast here that provide what the height of the storm surge was. For example, here in the western end of Lake Pontchartrain, there are 2 observations of 13 feet. So that means that the sea level there was 13 feet above mean sea level, which is basically a 13-foot storm surge in that area. So getting historical data like this together is very important to understand what is the storm surge potential for different areas and what kind of risks do they face. I also found that there were a lot of data that were provided by historical newspapers. So really, especially from the early to mid-1900s and on, we find a lot of scientific sources providing data. But if you get back to the early 1900s, back to the late 1800s, often newspapers provide some great data, especially for smaller storm surge events in rural locations or in cities as well. Here's an example of 2 articles from the Times-Picayune, which is New Orleans newspaper. The one on the left here is from July 1931. It says, accompanied by a driving rain, the gale kicked up a 6-foot tide that pounded the seawall and dashed over the coastal highway. This is talking about really a 6-foot storm surge that hit coastal Mississippi in 1931. Incidentally, when we go back in the historical literature, we never find the term storm surge before 1960. Pre-1960, they'll call it storm tide, or they'll just say the tides were 6 feet. This implies that there was a 6-foot storm surge. This one on the right says a majority of the residents of Freeport departed as a 60-mile-an-hour wind struck there late Thursday night, a dispatch stated. The barometer reading was 29.84 and the tide 4.5. So this is talking really about a 4.5-foot storm surge in Freeport, Texas, just south of Galveston. And so we could go back into the literature and find a lot of examples where scientific documentation, government documentation, academic literature, and historic newspapers provide storm surge observations. So we looked at this and we thought, there really are enough data out there to build a data set. We thought, if we're going to build a data set and for the Gulf Coast and maybe the whole country, we need a good name for this. And we thought, really what we want to do here is have water height observation data. That's what we want the data set to be. The problem with that is that if you're going to have a great data set, you need a good acronym. And every time we looked at water height observation data, we kept coming back to HOODAT, which actually happens to be the battle cry of the local football team, the New Orleans Saints. So, we thought maybe this isn't a problem. Sometimes the people up in Washington, they're sending money down here and they might not know what we're doing. And we thought, when we submit an annual report, we can just put a bunch of these HOODAT photos and they'll say, we don't really know what they're doing down there at LSU, but people seem to love this water height observation data. We'll just keep sending them a lot of grant money. So that's what I thought, but I was overvoted in our decision-making process, and we ended up calling the storm surge data set SurgeDat instead. SurgeDat has tropical cyclone-generated storm surge data from 1880 to present. So we have about 135 years of data there, and we now have over 8,000 high water marks for the U.S. We have the peak storm surge level, so looking at, for example, a hurricane and what was the highest storm surge in that event. We have 350 of those for the U.S. and about 700 around the world since 1880. So here's a snapshot of the U.S. Gulf Coast since 1880, and what we'll see here is that every circle on this map is a unique storm surge event. I just mapped out the peaks here. So this is the highest storm surge per hurricane, and really larger, darker circles are higher magnitude events. So, for example, our red circles here were at least 13 feet high. Our purple circles were at least 16.5. And we started to see, really, there is some kind of pattern to this. Along the northern and western Gulf Coast, we see a lot of these red and purple circles. We also see quite a few here in the Florida Keys. But if you notice along the west coast of Florida, we don't really see any. And so we really think that there's a reason for this pattern. One of the reasons is that the predominant track of hurricanes that we see through much of the season many of these storms travel from east to west across the peninsula of Florida. So when they're impacting the Gulf Coast, they're actually moving offshore, and they don't have as much momentum as when they move in the Gulf Coast. And then when we think of these storms like Andrew and Ike and Katrina, then they move over the open waters of the Gulf Coast and move towards, anywhere from Texas over through the Florida Panhandle. They have a lot of momentum, they're pushing a lot of water, and their strongest winds when they make landfall are actually blowing onshore. And so, sometimes in the Katrinas and Andrews, we've seen some wraparound winds produce maybe a 5 or 6 foot storm surge on the west coast of Florida, but then Katrina, for example, comes up here into coastal Mississippi and produces a 28-foot surge near Pass Christian. Incidentally, the highest two surges on this map, both were near Pass Christian, Mississippi. Katrina's surge was around 28 feet, and Camille's was around 25 feet. And so, again, we see really some kind of pattern there. It doesn't mean that we couldn't see a 20-foot storm surge in Tampa Bay. It just means that we haven't seen that historically since 1880. A limitation of this map is that every storm surge event is represented by just one circle on this map. And of course we know, for example, in 2008, Hurricane Ike flooded the northern Gulf Coast all the way from Texas to Florida, but it's just represented by the one purple circle there in Chambers County, Texas, where a 17.5-foot storm surge occurred. So what we started doing in 2012 was taking each of these storm surge events, like Ike, for example, and actually mapping out all of the observations for all of the events. And so this is what Ike looks like now in our more updated storm surge data set. So what we have here are more than 400 observations from Texas to Florida. The darker colored storm tides or storm surges represent higher magnitude events. So everything in red is 12 to 16 feet, everything in black is over 16. And we see really the peak surge was here in Texas. But you look along the coast of Louisiana, you still see a lot of 8 to 12-foot storm surges. Even south of New Orleans, you're about around 300 miles east of the landfall point for Ike, and you're still getting 8 to 12 feet of storm surge. So that's really spectacular, just seeing how much of the coast was inundated. And also look inland. I remember the day of Ike, I drove over to Orange, Texas. Driving by Lake Charles, I was about 25 miles inland at some points and saw quite a bit of storm surge flooding around apartment complexes, and this was about 25 miles inland. And so Ike also put a lot of salt water here up to the I-10 corridor. So that's another thing to consider with storm surge. Not only are we flooding the landscape, but we're pushing these surges in sometimes 20, 30 or more miles, and we're putting a lot of salt water on the landscape. So, for example, Vermilion Parish, Louisiana, took a lot of salt water on the rice paddies out there. You had the salt soaking into the soil, and then the following year was very dry, and so we had a lot of salt in the soil, and the rice yields were down considerably after both Rita and Ike. So this is something to consider if you're into ecosystems or ecology, if you're looking at duck or fowl habitats, or really anything in the food chain or agriculture. These surges sometimes will come inland considerable distances, and they're putting a lot of salt water on the landscape. So once we had these maps, like for example here with Ike, we realized we could overlay these maps into a mapping system or a GIS, and this is an experimental tool that we've developed. What I did here is I went into Galveston, Texas. I clicked on Galveston. I selected a buffer of 10 miles, and it gave me that circle with a 10-mile radius. That returned every storm surge observation within a 10-mile radius. If a given hurricane put 5 observations in that circle, it returned the highest one of the 5. And it gave me a whole history of storm surge here at Galveston, and it also on the fly, it calculated storm surge statistics. So it told me within this circle, the 100-year storm surge is around 17 feet. The 50-year storm surge is around 14 feet. And if I'm interested, for example, at a facility 10 feet above sea level, this curve here tells me that that facility will flood on average every 23 years from storm surge. So this is completely data-driven. This tool uses data from 1900 to present, and we feel like we have accurate data for about 91% of potential surge events in that 115-year period. So this tool is experimental, but we're starting to really see some use for this, understanding people's storm surge history at any location along the Gulf Coast. And we can build these histograms. So this is a histogram of storm surge history at Galveston, Texas. And, you know, it's interesting because what we see here is a common pattern with storm surge history. We've ranked here on the x-axis from 1 to 50. These are the 50 highest storm surges at Galveston. And on the y-axis, we have the magnitude in feet. And so we have the highest event was 20 feet in 1900. The second highest was 15.5 feet in 1915, and then we have Ike coming in here at number 3, around 11.5 or 12 feet. But we notice here a lot of these events are, you know, less than 5 feet, and then we see, you know, less events are 5 to 10, and then a few of these here really jump up above the others. And that's a common pattern that we see anytime we're looking at extreme statistics. And the reason why, for example, you need a very intense hurricane to hit right on Galveston to get this 15, 20-foot surge, or in Ike's case, a very large hurricane. But a lot of these here that aren't as high magnitude, they may be intense hurricanes that hit south or east of Galveston, or they may be weak tropical storms that hit right at Galveston. But again, it's very rare to get that really intense storm that hits right at the location you're measuring. And again, this is a common pattern found in statistics. An example, Bill and I were talking about statistics, and he said this is South Louisiana here that, he's out there at Lafayette, and he said if you're going to give a webinar, you have to talk at least about football. So I threw in the slide here. This is a common pattern, again, with statistics. This is all-time NFL passing leaders. I've ranked 1 to 100 on the x-axis, 0 to 70 up here on the y-axis. And again, we see there's not much difference between number 77 and 78, for example. The differences are very slight until you get up to these top few quarterbacks. And then, for example, Brett Favre, Peyton Manning, Dan Marino, these three up here really jump up above the others. And so, again, it's not that uncommon for someone to come into the NFL and have 5 good seasons and 1 great season, but for someone to come in and have 11 or 12 excellent seasons, it's very rare, and they'll often exceed the others by a substantial margin. And so when we think about storm surge history, that's important because going back to our history for Galveston, we look at these top 50 events since 1900. I've shaded the ones in blue that occurred since 1970. And so if someone moved to Galveston in 1970, they say, well, we've been here 44 years, we've seen a lot of weather, they would remember these surges in blue. And so if you look at this, they'd remember mostly these smaller surges, less than 5 feet, a couple around 5, 6 feet, and they'd remember a couple of these larger ones. They would likely think of Ike as a real outlier, around 12 feet, and they would probably think that's as high as the water can get. What they might not realize is that the 1900 hurricane produced a surge almost twice as high as Ike's. Again, these top few events are much higher than the others. And this is a concern in a place like Houston, Galveston, where their biggest events happened so long ago that most people alive do not remember them. So this is a way that we could construct history of storm surge and get an idea of what's happened and what the people, most currently alive today would remember. One last thing I wanted to close with is a storm surge climatology that I built for my dissertation. What this is showing is using this web tool that we built, we've taken 26 cities from South Padre Island around to Key West, Florida, and what we've done here is construct a storm surge climatology that considers storm surge return levels. So, for example, a 100-year storm surge return period, that's the level that we expect the water to get on average every 100 years. So it should equal or exceed that threshold every 100 years. And what we found here was we highlighted each of these locations with a bar with these varying levels of blue shades. The top of the highest blue is the 500-year storm surge level. Where the shading turns to darker color, we have a 200-year storm surge level. And then where the shading changes again, we go to 100, then 50, 25, and 10. The red dots within each of those bars are the actual observations that make up that statistical distribution at any given site. And so, for example, let's look here at coastal Mississippi. Site number 16 is Bay St. Louis. So this highest red dot is the height of Hurricane Katrina, and then the second highest is Hurricane Camille. When we go at city 17, this is Gulfport, the highest is also Katrina, and the second highest is also Camille. So many of these in eastern Louisiana over through Alabama, the highest red dot is going to be Katrina. And then we can kind of see where that fits along the graph of, according to this study that we did, Katrina was about a 130-year event there in coastal Mississippi. This is just considering, again, observed data since 1900. So there's no modeling here. This is a data-driven method. And the big picture that we really see here when we look at this map is that there's a lot of variability of storm surge depending where you are. So again, coastal Mississippi is an area that's very vulnerable. Also these bays in Texas, we get very high storm surge return periods. And also some locations like east of the Mississippi River levees here around Shell Beach, Louisiana, we also see some high values as well as the Florida Panhandle. But we see some lower values here in the western coast of Florida and also areas around like Morgan City, Louisiana. We notice that there are lower storm surge levels, and we don't feel like this is a mistake. We don't feel that we're missing much data. It's just very dependent on the direction that the coast faces. So, for example, Morgan City took a direct hit from Hurricane Andrew in 1992. But if you think about it, if a hurricane is positioned south of Morgan City, the winds around a hurricane blow counterclockwise, and so that's an onshore wind here at city number 11, Shell Beach. But in Morgan City, a wind blowing from east to west is actually blowing offshore and really keeping that storm surge level down. And so we notice these coastlines like around Morgan City, also the west coast of Florida, where they face west or southwest, typically tend to have lower storm surge levels than these areas that are open to the east, like around Shell Beach or Mississippi, and also coastal Texas. And one last thing too, the bathymetry or the water depth offshore also very much affects the storm surge heights. So this area here around eastern Louisiana and Mississippi, the water depth offshore is very, very shallow, and that leads to higher storm surge levels. So that's something called bathymetry, and that's also very important for storm surge generation. So one last thing to mention about this, the Gulf Coast observes some of the highest storm surge levels in the world. So when you're looking at even Morgan City or some of these places that see suppressed storm surge levels, that level in Morgan City or the west coast of Florida would probably be similar to the highest storm surges you'd see in northern Europe, around the Netherlands or Germany, and those countries have invested billions of dollars in flood protection. So really you can think of the Gulf Coast as storm surge on steroids. So if you're lower than Mississippi, you're still very vulnerable. Just Mississippi and parts of Louisiana and coastal Texas are extremely vulnerable to this hazard. So again, that's just a snapshot of storm surge climatology for 26 cities. And I just wanted to close with, looking at the impacts of this. Obviously, storm surge impacts many industries like fishing and seafood, beaches and resorts, coastal development, oil and gas, and then again, many ecological impacts as well, because we're putting a lot of this salt water very far inland, and it's salty, and it really affects the ecosystem sometimes for a long time. So I wanted to close with a few questions for discussion. We've developed this storm surge data and analysis, but we're very interested in collaborating and working with many different groups out there. So we'd love to hear, for example, how might storm surge impact your area of expertise? What are your information needs about this hazard? For example, some of these statistics that we ran, could that information be helpful to you? And if so, how would you like that information presented? And then where do we go from here? Could we have some follow-up conversations after the webinar? What about collaboration on projects? And what about other ideas you might have or questions that you might have? Before we get into that question and answer time, I just wanted to provide my contact information. Again, I'm funded by SCIP. If you go to southernclimate.org, you'll get to the SCIP website. Storm surge is just one of the hazards that we're looking at. That's one of the more coastal hazards. We also do a lot with any kind of climatology, rainfall, drought especially, severe weather, things like that. And you can find SurgeStat at surge.srcc.lsu.edu. My name again is Hal Needham. I'm based here at LSU. My email is hal@srcc.lsu.edu. Please send me an email if you have any questions or ideas of how we could possibly work together in the future. So that's everything I have today. I'd love to open this up for a little discussion, or again, maybe we can talk about some of these questions I've posed near the end of the presentation.
Thanks much, Hal. We have time for questions, and we thank everybody's patience for being here. Give Hal a chance to catch his breath. If you have any questions, feel free to put them on the chat box or chime in now on the phone. Do we have any questions out there?
This is Allison, and I'll jump in. I'm just for your information, I'm with the USGS, and I sit for the Southwest region on our storm team, and Southwest region includes Texas, and in my previous reorg, I also had Louisiana as one of my states, and I'm just wondering, as you're pulling in some of the data that's been collected from the USGS rapid deploy elevation systems that we put out, are you finding some of that information is more useful than others, or is there something that you would think, well, gosh, if we had only thought to deploy it in a different pattern, we would have a better data set?
Well, that's a great question, Allison. What's particularly very useful about the USGS data is that you know, we have teams of people going out there and deploying these gauges in a very dense network. So, you know, typically along the coast, we do have long-term tide gauges, but they tend to be spread out pretty far. And so what I really love about the USGS data is that you'll have teams going in and, you know, obviously, as you know, putting up sensors, you know, strapped to bridge pilings or piers or, you know, really it seems like wherever they can get a stable location. From what I've seen with the USGS data, it's very dense, it's very helpful. I haven't particularly thought about would it be better to deploy it in a different way. It seems like they're doing everything they can to really get in there and deploy them as densely as they can around the area of the greatest storm surge impact. I guess they really focus on the area where they expect the peak surge to be, which I think is where we need the most dense network of data. So I just have to say thumbs up to USGS. I think the work that y'all are doing is very valuable and helpful, and you know, I've just seen a lot of good things. I don't really have any criticisms or suggestions of how to improve.
Do you have a feeling for if we're going far enough inland?
Yeah, that's a good, you know, because once we start to get inland, I think we start picking up, already there'll be river gauges going inland considerable distance, and I know the Army Corps often has a lot of river and stream gauges going inland as well. So from what I've seen too with storm surge, the most localized effects of surge tend to be right on the coast. So I think, you know, and USGS does go inland. I think sometimes there'll be gauges, you know, 5 or 10 miles inland at least. So I think everything's going pretty well with that. I think there already is sort of a fairly dense network of gauges going up rivers and upstream. So I think they sort of capture what's happening inland as well. So I think it's going pretty well right now.
All right, thanks.
Hal, this is Bill Bardish. You've still got control of the PowerPoint, and it might be beneficial to keep those questions on the screen that you had.
Yeah, sure.
And I think maybe folks on the phone line might want to refer to those questions for Hal.
Okay.
Any other questions for Hal?
This is Melanie Driscoll. I'm with the National Audubon Society. We've recently released climate change models and how they will be potentially affecting bird populations across the United States. The models are fairly focused on temperature and other weather data, but have not yet incorporated other factors like land cover, potential future land cover, or sea level rise. We're starting to work on kind of a version 2.0 and including things like sea level rise, which will obviously affect where future habitat might be. I'm interested in starting to think about whether it's valuable to add in storm surge data to the modeling. So I don't have a real specific question beyond, do you think that that might be helpful? And then maybe to follow up with you a little bit down the road with it.
Yeah, thanks, Melanie, for that question. And I'm really glad that you mentioned sea level rise, because sea level rise and storm surge, they're really coupled hazards. You almost have to include one if you're going to include the other, so to speak. And that's something I forgot to mention. For example, when I showed that storm surge climatology, you know, we could see the bars for coastal Mississippi were like off the chart, whereas an area like Morgan City, Louisiana had less of a risk from storm surge. But if you look at sea level rise, it's really the exact opposite for those two places. Places like Morgan City, Grand Isle, Louisiana, these places have some of the fastest relative sea level rise rates in America, whereas coastal Mississippi is much more stable. The land isn't subsiding or sinking as quickly. And so I think it really is important when we look at storm surge to consider sea level rise and the other way around, because it's really going to be a combination. You know, as the seas rise, we're going to have more coastal erosion. We're going to be more vulnerable to storm surge. But then again, in some of these areas where we see like rapid sea level rise, we might not see as high storm surges, and we might see vice versa. So I would love to talk to you about that. I think it's important to consider both, because both of these hazards really do work together, so to speak.
Okay, that's really helpful. I will not be the lead on that, but I'll go ahead and email you my contact information and maybe start to loop you into some discussions.
Yeah, thank you, Melanie. And one more thing to say with that, often we tend to think of storm surge as being just connected in with hurricane strike climatology. So we tend to think where you have more hurricane strikes, you get worse storm surge. And what we're seeing here in the study is that's not necessarily the case. My academic advisor, Dr. Barry Keim, he did a detailed study of hurricane strike climatology, and they found along the Gulf Coast the most vulnerable areas to strong hurricane winds are actually southwest Florida around Fort Myers and Key West, as well as western Florida around Pensacola and even around Mobile, Alabama, Dauphin Island area. Those are the areas of the Gulf Coast that are most vulnerable to strikes from strong and experiencing high levels of hurricane winds. However, storm surge tends to be more of a problem along the northern and western Gulf Coast, around Mississippi, Louisiana, and Texas. And so really, we almost need to decouple these hazards of wind and surge, and we can't just look at modeling for hurricane strikes to get an idea of where storm surge might happen, because really it's much more complex than that. And we need more than just a hurricane. We also need, it depends on the direction of the coast. It depends on the bathymetry or the water depth offshore. And so I think for a modeling perspective, it's really good to look at storm surge almost as a separate thing, away from just looking at where we might see hurricane strikes, if that makes sense. So yeah, I would love to work with you all on that. It sounds like a really important project.
That sounds great. Thanks for the explanations, and I will go ahead and email after this.
Hal, we had a question pop up on the chat box. I'm not sure if you can see it, but what it is there any evidence in the 1850 to current data set of increasing frequency or magnitude of storm surges?
Yeah, that's an interesting question, because what we definitely are seeing is an increased level of seas. We see sea level rise along most of the U.S. coast, and so and also some of the models have suggested, or scientists are suggesting, that we may see more intense hurricanes in the future. So an important question is, have we seen a long-term trend in storm surge magnitudes? I looked at that actually when I did my master's degree here. I think at the time we had 130 years of data, and I actually split that data set into the first 65 years and the second 65 years, and I actually found the exact same number of surges over 10 feet in both of those two periods. So in other words, the first 65-year period and the second 65-year period had the same number of large surges. When we get to the smaller surges, we see more surges more recently, because if you get, say, a 6-foot storm surge or a 4-foot storm surge from 1885, it probably didn't survive the historical record because it wasn't significant enough. So just looking at the higher magnitude surges, we did not actually see any trends. And so I'd say right now we don't really see a statistical trend in that, but we do definitely see a statistical trend in sea level rise, and that will exacerbate erosion and also make storm surges more severe as well.
Any other questions for Hal out there?
Hal, this is Charlotte Renz with the Nature Conservancy. Can you guys hear me okay?
Yeah, I can hear you fine.
Okay, so the Nature Conservancy owns quite a number of preserves right along the coast, and we're starting to do some climate change scenario planning, thinking about what these places might look like 50 years from now. And I was wondering if we could maybe contact you for some of the output from that experimental interface you showed us with Galveston, with the return intervals of the different height storm surges, because I think that would be really helpful for our planning efforts.
Absolutely, and I'm glad you mentioned that. And something I would like to clarify, I gave a website for SurgeDat. If you go to that website, you'll find some maps, you'll find data. In fact, there's an interactive web tool where you can look at storm surge history since 1980, and those are more recent data that we know are very accurate. They've been quality control tested. What you mentioned, Charlotte, was access to this experimental tool that we're developing. If anyone would like access to that, please email me. I would love to send you the website, the username and password, just so you can start to play with it and so we can get an idea of, you know, we want to test this out and do some beta testing first. So Charlotte, just contact me. I would love to send you that username and password, and that goes for anyone else as well on this call.
Great, thank you.
Any other questions for Hal out there? If not, please feel free to contact Hal either through us or through the information he left on the screen. Again, this is Bill Bardish with the Gulf Coast Prairie Landscape Conservation Cooperative, closing out this noon webinar series for November, reminding you that we have another conference call webinar next month, December 3rd, same time, noon. And we'll be talking more about the Gulf Coast and some of the conservation efforts and restoration efforts on the Gulf Coast. Hal, any last words before we sign off?
Nothing really comes to mind. I mean, I just appreciate everyone tuning in. And again, this is something that we're continuing to develop and work on. If anyone, you know, has any suggestions, we'd love to hear really what people's needs are. And one very last detail. I forgot to mention, I think all 5 of those quarterbacks in there played for LSU. I think so. I don't have confirmation, but I think that's what I heard.
I think that's pretty close.
Well, thank you
anyway,
thank you for your patience today, and thanks for everyone attending and the great questions and interaction.
Thank you all. Have a good day.